Welcome DEKWP, Xiaogong Abor. Your learning journey starts now. Ever felt like some math problems are just stubbornly unsolved? Take Goldbach's conjecture. Simple statement. Every even number bigger than 2 is the sum of two primes. Easy peasy, right? Wrong. It's been bugging mathematicians for centuries. Why? Because primes are like mischievous kids, their distribution is all over the place, and checking every possible pair for infinite numbers. That's a combinatorial nightmare. Traditional methods hit a wall. So, what if we're looking at this all wrong? Alright, let's switch gears. Forget just crunching numbers for a second. Enter semantic math, a framework that builds understanding from the ground up. Think of it as building meaning, not just equations. We use the DIKWP model, data, information, knowledge, wisdom, purpose, to dissect concepts. Key ideas here are bug awareness. Basically, recognizing gaps or inconsistencies in our understanding actually drives us to find better solutions, like debugging code. And semantic tension, the idea that concepts have inherent structures, sometimes imbalanced, and they naturally seek resolution. The guiding principle, Occam's razor, the simplest explanation, often the most elegant, is usually the right one. This isn't just philosophy, it's a tool. Now, let's redefine our basic building blocks through this semantic lens. Even numbers, they're fundamentally symmetric. Think n plus n. Perfectly balanced, zero internal tension. 7? That's an odd number. It's inherently asymmetric, always having that leftover one. You can write it as m equals n plus 1. That extra one is the semantic tension. Primes? These are the indivisible atoms of multiplication. In our additive context for Goldbach, they're the fundamental units, the lowest level of complexity. Crucially, except for 2, all primes are odd, meaning they carry that plus 1 tension. 2 itself is special, both even and prime, perfectly symmetric and atomic. This reframing is key. So, how does this solve Goldbach? An even number, being perfectly symmetric, must be constructed from components whose tensions cancel out. What cancels out the plus 1 tension of an odd number? Another plus 1 tension. So, odd plus odd equals even. This naturally leads to the idea of pairing odd primes. But why exactly 2 primes? That's where Occam's razor shines. Any other way to build an even number from primes gets complicated fast. Using 1 prime? Impossible for evens greater than 2. Using composite numbers? They ultimately break down into primes. Using 3 or more primes. Redundant. For example, 2 plus p plus q, where p and q are odd, implies p plus q is even, which is back to the 2 prime case. The 2 prime sum is the most economical, simplest structure. The semantic system itself, driven by the need to resolve tension and avoid redundancy, forces this pairing. It's almost inevitable. So, what's the takeaway? From this semantic perspective, Goldbach's conjecture isn't just a random pattern found in numbers. It feels like a fundamental law of the integer system, a consequence of how we define evenness and primality semantically. It's less about complex combinatorics and more about a principle of semantic compression and conservation. It suggests that sometimes the deepest truths in mathematics lie not just in the symbols, but in the meaning we construct. This approach might even hint at how future AI could potentially grasp mathematical intuition beyond mere formal logic. Food for thought, isn't it?